Welcome to module 4 of this course, Time Dependent Quantum Chemistry. In this module, we will go over we will try to find out the connection between quantum mechanics and linear algebra. And realization of that connection will help us build the platform to perform to obtain numerical solution to the time dependence Schrodinger equation TDSE. Why we need numerical solution? Because I have been telling you in the last since last module that always we may not get the analytical solution. For free particle wave packet dynamics, we have been able to get the analytical solution, and we have got the general solution also for that wave packet. But let's say the wave packet doesn't have a Gaussian form. It has entirely different, very complicated form. How do you deal with those kind of form? Let's say I have a Gaussian form, but the particle is experiencing very complicated potential. So in that case, we will not be able to get the analytical solution. We need to rely on the numerical solution, and to reach there, to understand how numerical implementation will be done of TDSE, we need to understand the basic connection between quantum mechanics and linear algebra. So that's exactly what we're going to do in this module. In the previous module, where we have discussed this wave packet dynamics, we have analytically solved dynamics of a free particle, and in the tutorial we will see that the Gaussian wave packet dynamics can also be solved with linear and quadratic potential as well. So Gaussian wave packet dynamics is for many aspects of Gaussian wave packet dynamics, one can use analytical approach to solve the problem. But for any arbitrary potential, this analytical approach will fail, and we have to rely on numerical approaches. In fact, a number of quantum dynamics problem that can be solved analytically is very limited. Therefore, it is quite instructive that we begin a discussion on the numerical approaches which will enable us to explore quantum dynamics for any arbitrary potential. So that's the motivation here. Numerical solution to the TDSE is a gigantic subject. It's a huge subject, and but it is fundamentally developed based on matrix representation of quantum mechanical equation. This numerical approach we need matrix representation of quantum mechanical equation. So numerically we will be dealing with matrices. That's why we need to represent quantum mechanical equations in the matrix form. And these numerical methodologies is developed based on the realization that mathematical language of quantum mechanics is actually linear algebra. Mathematical language of quantum mechanics. So in this module, what we'll do, we will develop a coherent sense of wave function and the operator. Wave function and the operator. Wave function and operators. See, these are the two key constituents of quantum mechanics. So if I want to implement numerical if I want to obtain numerical solution to quantum mechanical problem, first I have to learn how do I numerically represent this wave function and operators, because these are the two things we'll be dealing with in quantum mechanics. And that's why what we'll do, we'll develop a coherent sense of the meaning and the properties of the wave function and the operators from linear algebra point of view in this module. We'll begin with reviewing intriguing general properties of quantum mechanically acceptable wave functions and operators from linear algebra point of view. Then we'll present basis set approach to quantum mechanics, which will give us matrix representation of the wave function and the operator. And in the end, after briefly reviewing matrix algebra, we will present methods to obtain eigenvalue and eigenfunctions of a quantum system, making use of grid representation. We'll show that also. What does it mean by grid representation? So in the end, the discussion in this module will lead us to the place where we'll be able to perform numerical, we'll be able to get the numerical solution to the TDSE. So let's begin with the general properties of a function from linear algebra viewpoint. All well-behaved wave function which is acceptable in quantum mechanics must be square normalizable. This is something which we have without noticing it, we have used it. We have used normalization condition. We have said that before the time evolution, we must look at how we must take the normalized wave function always. So, all well behaved or acceptable, physically acceptable. Any function I cannot accept physically in quantum mechanics. Those functions which can be accepted in quantum mechanics is called physically acceptable wave function. Wave function that must be square normalizable. And what does it mean by this square normalizable? That means that if I have the wave function to be psi x, for the time being I can think about, okay, forget about this time dependency right now. We are just thinking about the space dependency, because time part comes as a phase factor, so it's not an issue. So if we look at this wave function, then this square normalizable, it has to be square normalizable. What does it mean? It means that this integration minus infinity to plus infinity, I have to immediately take that wave function. I have to, if I want to check whether this wave function is usable in quantum mechanics, then immediately I have to find out this integral psi star psi dx. This is nothing but minus infinity to plus infinity f square of the absolute value of psi dx is 1. It should be 1. This is called normalization condition, but when it is 1, psi is normalized. But always psi may not be normalized, we have to make it normalized, and in that case if it is not normalized, still it is acceptable in quantum mechanics, as long as this integral minus infinity to plus infinity becomes real positive constant and must be less than infinity. So this integral, so first question is that if somebody is proposing that, okay, let's assume that this wave function is the solution for a particular quantum system, then immediately we have to check whether this wave function, the proposed wave function, is acceptable as a solution in quantum mechanics. And how do I check that? I can check it by taking this integration and finding out whether this integration giving me a real positive constant value. If it is not giving real positive constant value, if it is becoming 0, if it is becoming, let's say, real constant positive, finite constant positive value, okay, if it is becoming infinite, so I cannot accept it. I cannot accept that wave function. So for an example, this is just an example, we have seen that a Gaussian function, this is an example, we have already seen this example. A Gaussian function e to the power minus ax square, this function, within this minus infinity to plus infinity limit, it is a well behaved wave function. This is acceptable wave function in quantum mechanics. But we have already seen that e to the power I kx, when we try to normalize it, when we try to get this square normalization condition, we have found that within this limit minus infinity to plus infinity, this is not acceptable, because within this limit we have got infinite value. If we take this integration minus infinity to plus infinity e to the power I kx dx, it gives this is square modulus, so this is going to be e to the power minus I kx, then e to the power I kx, then dx. This is going to be infinite. So this integration becoming infinite, so this function cannot be used in quantum mechanics. So one thing we have to remember, that I can propose a wave function, but I have to in the end definitely need to check whether that wave function is acceptable in quantum mechanics, and whether it will be acceptable or not, that can be checked by taking this integration and finding out whether I am getting a real constant positive value. One interesting mathematical fact about all square normalizable wave function is that they all follow property of linear vector space, and the reason why it should be this is that if we take only wave function which is square normalizable, then those wave functions, acceptable wave functions, will follow the property of linear vector space, and that is why we can use linear algebra. So in order to use linear algebra, or this linear vector space also called, sometimes called Hilbert space, both are, this is just mathematical language. We say that okay, those wave functions which can be acceptable in quantum mechanics, they live in Hilbert space. Hilbert space is a mathematical space, it is a hypothetical space, let us say, where these wave functions are living. It is more like we are living in solar system, and if any living being is living in solar system, they will follow the similar property. So similarly, if the wave function is living in Hilbert space or linear vector space, it means that it must be square normalizable. There is a consequence, and that is the reason why I can use linear algebra. Otherwise, I cannot use linear algebra. So I have to start with always square normalizable wave function. Second property of wave function from linear algebra viewpoint is that if psi 1 and psi 2 are square integrable, which is square normalizable functions, which means that I have a vector space, linear vector space, let us say this is a space, this is called Hilbert space, let us say, And in this Hilbert space, if psi 1, psi 2, psi 3 all are living, then we have to remember that in the same Hilbert space, their linear combination, any linear combination will also live in the same Hilbert space. So if psi 1, psi 2, dot dot dot, many other functions, square integrable, all square integrable functions are living in the Hilbert space, any linear combination of these wave functions are also square integrable, square normalizable. So what it's suggesting that as long as the wave functions are sitting or living in the Hilbert space, their linear combination will also live in the same Hilbert space. And we know that anything which is living in Hilbert space would be square normalizable. I can normalize it, which means I can accept it as a solution to the solution in quantum mechanics. Because one defining condition of Hilbert space is that both functions and their linear combinations should be part of that Hilbert space. And if it is so, then if I have a solution of psi 1, psi 2, individual solution of psi 1, psi 2, psi 3, dot dot dot, then and each one is square normalizable, then I should have another solution psi 1 plus psi 2, that is also would be square normalizable. I can take different kind of combination. This is also square normalizable. I can take psi 1 plus psi 4. This is also square normalizable. All linear combination will be square normalizable. So this is also, if they are acceptable in quantum mechanics, then they are also acceptable in quantum mechanics. And this is something which, without noticing it, we have used it already. In the first module, we have checked the linear combination. In the second module, in the third module, when we have proposed the wave packet, we have already taken linear combination of different waves, the plane wave solution. So these were the plane wave solutions, and we have taken linear combination to make this acceptable solution. So this is a quite common thing in quantum mechanics, and the reason why we can do that is the property of the Hilbert space, the mathematical space we have defined. Third property of the wave function is going to be inner product. Inner product, what is inner product? I will just show. Inner product of two wave functions living in a Hilbert space is a measure of their overlap in that Hilbert space. So inner product is nothing but the overlap of the wave function, which is given by minus infinity to plus infinity, this integration psi 1 star psi 2 dx, and if I take the complex conjugate of this, then it will change the order as psi 2 star psi 1 complex conjugate. So what is the meaning of it? It means that in the Hilbert space, if I have two wave functions psi 1 and psi 2, and if we find out this integration, then this integration shows how much overlap they have. Let's say psi 1 and psi 2 is represented by these two ellipse, this kind of function, psi 1 here, psi 2 here. So, overlap means how much a space it is occupying and sharing the space, that is called overlap. This is the overlap part, and this integration will show how much overlap we have between two wave functions in the Hilbert space. What it suggests that the inner product always exists as long as both functions live in Hilbert space. Because these two functions are living in Hilbert space, their inner product will definitely exist. It will not happen that this integration will become infinite. It will not happen as long as this wave function is sitting in the Hilbert space. So, the basic idea, mathematical background for this is that the inner product always exists as long as both functions live in the Hilbert space. So, that is the property of the Hilbert space. This is inner product, and another property of the function is going to be the norm of the wave function is given by this integration minus infinity to plus infinity psi star psi dx to the power half. This is the normalization constant. So, if I want to normalize a wave function, all I have to do is that psi divided by psi, norm of the psi. This is called, this I will get the normalized wave function. This is the way one can get the normalized wave function. And if this part, this integration is becoming 0, it means that these two functions are orthonormal. So, these are the properties which we have already used. Orthonormal wave function already we have used, but we have not noticed that we are using it as a consequence of the Hilbert space, the property of the Hilbert space, and this is something which we are pointing out. Now, we will move forward to the operator, but before we move forward to the operator, one interesting point will be raising here. Let us assume that I have a wave function psi x equals x to the power half. This is a wave function, and we are saying that, and question is whether this wave function, now if I have a wave function, a function x to the power half, I would like to know first whether this wave function lives in Hilbert space, because if it is living in Hilbert space, it would be useful in quantum mechanics, whether it can live in Hilbert space for the interval 0 to plus 1. So, all we need to do in order to check that, what we need to do, we have to find out this integration x to the power half, this is real. So, x to the power half multiplied by x to the power half dx, this integration which is nothing but x minus infinity to plus infinity dx, which is nothing but x square by 2. The limit is not minus infinity to plus infinity, limit is given 0 to 1. Different limit may have a different Hilbert space. So, within this limit, I would like to check whether I can construct the quantum mechanics within this limit. So, limit is not minus infinity to plus infinity here, we are considering 0 to 1 limit, and we say that this value is going to be half. This is a finite constant, positive constant. So, this function can live in Hilbert space, and if it is living in Hilbert space, for this limit I can use it in quantum mechanics only for this limit. I did not check for other limit. So, I will construct the Hilbert space. This is my Hilbert space. It is more like, I told you, more like a solar system, let us say. All human are living in solar system. This is your solar space, let us say. So, no matter which human you pick up, they will have similar kind of property. They have 2 hands, 2 legs, 1 head, similar kind of property. Similarly, in this mathematical space, Hilbert space, if one wave function is sitting here, then that will follow the property of the Hilbert space, and the property of the Hilbert space suggests something, and that suggestions we are actually using in quantum mechanics. So, that is the connection between quantum mechanics and linear algebra. So, we have already seen that this within this limit, this wave function x to the power half is living in Hilbert space. So, it will be useful in quantum mechanics, very nice. Now, in quantum mechanics we know that some operator will be acting on it. Let us assume that my operator is d dx, derivative operator, very simple derivative operator which will act on this x to the power half, let us say. When operator acting on the derivative operator, x to the power half, what will happen? Immediately I will get x to the power minus half, and the limit is, to define this Hilbert space, I have considered the limit is going to be 1 to 0 to plus 1. That is the defining condition for the Hilbert space, for this particular Hilbert space, not for all Hilbert space. I can define another Hilbert space for a different limit, but within this limit I am defining this Hilbert space. What I see is, now I have got another wave function. So, an operator acting on wave function, and I am getting another wave function, and I have to check whether this new wave function, which is now call it phi, whether that also live in the same Hilbert space or not. That is the first thing we will check, and in order to check that, what we need to do, we have to again carry out this integration minus infinity to plus infinity, this is the limit is not minus infinity to plus infinity, is 0 to 1, x to the power minus half, x to the power minus half dx. We get 1 by x 0 to 1 dx, which is ln x 0 to 1, which is minus infinity. Whenever I have this integration to be minus infinity, minus infinite or plus infinite, then we cannot say that this wave function is living in Hilbert space. So, what is going on? I had a wave function which was happily living in Hilbert space, an operator acted on it, and it made the function to be out of Hilbert space. That function cannot stay in the same Hilbert space anymore. It is going out of the Hilbert space. This causes a problem, because if a function is going out of the Hilbert space due to an action of an operator, then I cannot use it in the same quantum mechanics. In order to use the wave function in the quantum mechanics, I need to have the wave function living in the Hilbert space all the time. Does not matter whether any operator acting on it, it can act, an operator can act on it. The defining condition of using that Hilbert space is that any time the function which I am using as a solution of the quantum system, that should stay in the Hilbert space. In addition to that, if an operator acting on that wave function, the new wave function should also stay in the same Hilbert space. That is the defining condition. So, what we see that there are certain kind of mathematical operators such as derivative operator, which we frequently use, can actually take an operator and a wave function living in the Hilbert space out of the Hilbert space, and that is not acceptable. So, this kind of operator cannot be used. So, there are restriction in what kind of operator I should use in quantum mechanics. It should be restricted. It should not a function living outside the Hilbert space does not carry statistical interpretation anymore, and this is why becomes useless in quantum mechanics. So, the basic idea is that when I am selecting a wave function, that should stay in the Hilbert space, because it will then carry statistical interpretation, and that is the only interpretation I have for the wave function in the standard interpretation in quantum mechanics, statistical interpretation. If the statistical interpretation is gone, so then there is no wave function, meaning of the wave function, and if there is no meaning of the wave function, there is no quantum mechanics anymore. So, that is why the wave function has to live in the Hilbert space, and if an operator acting on that wave function living in the Hilbert space, if it is taking out of the Hilbert space, then that is also a problem. Then we have lost the interpretation of the quantum mechanics again. So, everything has to be in the Hilbert space, and that is why operator space needs to be restricted. We cannot use any operator to control to work in quantum mechanics. So, let us find out what kind of operators we can use and what are the operations of operators we can think of from linear algebra viewpoint. Inverse of an operator will be given by, let us say, A inverse of A is defined by A inverse. So, what happens? A acting on psi giving me another wave function. In that case, inverse of A phi is giving me psi. This is more like a reversible process. Quantum mechanics, in this from this point of view, quantum mechanics is reversible. If this operator is acting on psi and giving me phi, then inverse of this operator can act on phi and I can get psi. So, this is one property of the operator which we will be using in quantum mechanics, and this is directly coming from the property of linear vector space, linear algebra, or Hilbert space. Or in other words, I can write down A acting on psi is phi, or A, the psi can be written as inverse acting on phi equals phi, and this is only possible when this A inverse equals 1. So, this is an operator which is suggesting that you multiply by 1. So, this is another property of the inverse of an operator. Adjoint of an operator, what does it mean? Adjoint is defined adjoint of A is defined by a dagger such that A dagger will be considered to be adjoint of A when this will hold phi star A psi dx equals minus infinity to plus infinity A dagger phi whole star psi dx. When this relation will be satisfied, then we can say that A dagger is adjoint of A. So we have to take few examples to show that adjoint of an operator, and we will take one example. Let's say we find out adjoint of an operator X. If we take X operator, then what will happen? So let's say I start with X operator. X operator is nothing but multiplied by S. So I'll check with minus infinity to plus infinity phi star x psi dx. That's my integration. Now X is a multiplication operator. So I can place X anywhere. Remember, when you are dealing with an operator, let's say I'm dealing with this differential operator acting on psi, and on this side I have phi. If I'm dealing with this kind of operator, derivative operator, this derivative operator means it is operating only on psi. It is not, it cannot be just, the position cannot be changed without any constraint. I cannot write down this ddx. It is not possible. Operator acting on this. But if it is a multiplication operator, then I can replace it anywhere. It is just multiply. So I can place this conveniently here, X, it is the same value because it's a multiplication operator. So I can, and X is real, so I can also write down X phi whole star, because here X star equals X, because X is real and X is multiplication operator. Psi dx. You see, we have now, this is fulfilled. This form is equal to this form. Because it is fulfilled, I can say that X is adjoint of X. It is the same actually. So X operator is equal to its adjoint. They are the same. It doesn't change. Now we will check a derivative operator. Let's check with the derivative operator whether we get what kind of results we get for derivative operator. So we have already, I'll write it down, that X operator is equal to its adjoint. They are equal. For the derivative operator, let's say I have an operator which is d dx. If this is the operator, then I can try to find out minus infinity to plus infinity phi star a psi dx equals minus infinity to plus infinity phi star d dx psi dx. Now I cannot just position this operator anywhere without any constraint. It is not possible. This operator only acting on this. So I have to go for integration by parts. and integration by parts, if I do that, then I get phi star psi minus infinity to plus infinity minus infinity to plus infinity d dx phi star psi dx. This is integration by parts, and the general formula of integration by parts, I'll just remind, it is if I have limit a to b, u v dash is the derivative dx, then this is going to be u v a to b minus a to b u dash v dx. That's the general general formula of integration by parts, and that's exactly what we have done here. And so what I can write, and now this part is going to be 0. Why? Because I said that phi and psi are in Hilbert space, and if they are in Hilbert space, they has to be square normalizable. In order to be square normalizable at infinite, their values should be 0. This is all coming from the property of the Hilbert space. So this part, this integration will be, this part will be 0. Then I have plus minus d dx minus infinity to plus infinity d dx phi whole star psi dx. I have now the relation fulfilled. This one, this part is here and this part is here. But what is the difference right now? I have now the a dagger adjoint of this operator is nothing but minus d dx. So what we see here is that if it is derivative operator d dx, then a is not equals to its adjoint. So it is not necessary that the adjoint would be the same as the operator always. It depends on the operator, what kind of operator I have. One can very easily prove that if the operator is I d dx, then it will be equal to its adjoint. One can prove this. So with this idea, what we are seeing is that adjoint can be found analytically with this expression, with this integration, and one can find out different operators whether that will be adjoint, what would be the adjoint, and sometimes I may have a situation where its adjoint would be equivalent to its own operator form. We will stop here and we'll continue this session in the next class.